Hey everyone. Today it's my privilege to talk about our work where we built a theory that allows us to systematically design internet congestion control algorithms in a way that we can provide provable performance guarantees about the algorithms we design. Not only this, our approach also allows us to discover and prove impossibility results in congestion control. Over the past few decades, our community has invented tons of congestion control algorithms, or CCAs in short. Each one of them identifies when prior algorithms fail and propose new ideas to resolve the issues. In this work, we take a step back and ask, what will it take to put an end to this never-ending cycle and build congestion control algorithms that don't break in surprising ways? In answering this question, we found that the problem lies in the way that we've been building congestion control algorithms. Traditionally, CCAs look like this. They take as input some feedback from the network and maintain statistics to track the state of congestion in the network and determine a sending rate. And our community has defined a myriad of statistics for this purpose. For instance, they look at delay gradients, ACK rates, and so on. There's no consensus on which statistics work best. The problem with these ad hoc statistics is that they invariably make some implicit assumptions about the network, leading to two key issues. First, these ad hoc statistics commit false negatives, in the sense they'll overlook considering network behaviors. For instance, let's say a congestion control algorithm saw that the RTT of an acknowledgement increased. Many CCAs will just blindly react to this measurement without considering what could have caused this measurement and what will be the consequences of their reaction. Such an RTT could have been produced due to some self-induced queuing. It could be due to some decrease in the link rate, or even reasons unrelated to congestion. For instance, there may be some delayed ACKs or ACK aggregation. The congestion control algorithm's optimal response is different in all of these situations. And depending on how exactly a given congestion control algorithm responds to this inflated RTT measurement, it may only consider a subset of these explanations. What's more is, even if CCAs consider all of these explanations, they may commit false positives. So they may fail to disambiguate between these explanations, even when disambiguation is possible. So we looked at the RTT measurement. We'll get a clearer picture if we look at all the observations a CCA made, represented through the time series of sending and acknowledgement sequence numbers. Here, the slope of the red and blue lines respectively show the sending and acknowledgement rates. And the time between sending a sequence and receiving its acknowledgement gives us the RTT. In this graph, the sending rate increased, implying some self-induced queuing. The exact same RTT inflation could have also been produced due to a decrease in ACK rate, implying link rate decreased. Again, the same RTT could have also been produced due to some stalls in the packet processing with the same average ACK rate, implying delayed ACKs or ACK aggregation. And so really, to make informed rate decisions in congestion control, we want to be consulting this time series of sequence numbers. However, directly making interpretations from this time series is hard. That's why we had so many ad hoc statistics in the first place. The information congestion control algorithms really care about from this time series is what does it tell them about the state of what's going on in the network. And so we've built a method to summarize the time series into a representation that exhaustively describes the possible states of the network. We call this representation the belief set, and it looks something like this. It describes the network state in terms of the possible latent parameters of the network. For instance, what could be the bottleneck bandwidth, bottleneck buffer size, queue occupancy, propagation delay, and so on. Here, for visualization purposes, I've just shown 3 dimensions. A point here on the blue surface describes a parameter combination that can explain the time series of observations made by the CCA. And since there may be uncertainty or ambiguity in the parameter combinations, we get a set of multiple such points. So how is this summary any different from the ad hoc statistics that congestion control algorithms have defined? First and foremost, the belief set provably extracts all useful information from the time series of observations. We formally prove that if there exists a deterministic CCA or a CCA that can look at the entire time series to make rate decisions, so if such a CCA can ensure an objective constraint, then there also exists an equivalent belief-based CCA that can also ensure the objective, where the belief-based CCA can only look at belief set to make the rate decisions. So we can just throw out the time series out the window and just look at belief set, and we don't give up anything from this simplification. Second, the belief set gives an accurate characterization of the network conditions. It does not overlook network conditions and disambiguates between explanations as much as possible. Third, we don't make any ad hoc decisions when we're computing this belief set. We mechanically derive it from a model of a network where we explicitly state any assumptions we make about the network. And so before I exactly describe what assumptions we make and how this mechanical derivation works, I want to describe what the belief set buys us. Belief set provides us two key benefits. First, it simplifies the design of congestion control algorithms. Traditionally, CCAs will conflate statistics and rate computations. And so CCA designers often have to do this mental juggling of how changing their statistic will affect the rate computation and vice versa. With beliefs, we decouple these two into two independent parts. In the first part, we just look at what the time series of observations tells us about the state of the network. And in the second part, we need to decide a rate given that the possible network conditions are already summarized by the belief set. To do this, a CCA can simply run each network in the belief set in their head, compute the outcomes of different rate choices, and pick one that gives them the best utility across the networks in the belief set. This is a purely stateless task, which makes it amenable to automation, as I'll talk about later in the talk. The second benefit of belief set is that it helps us formally reason about trade-offs in congestion control. At any given time, an algorithm has made some observations which we've summarized into belief set. Here, I'm just showing 2 dimensions for ease of visualization. Now, using the summary, the CCA chooses a rate and gets some observations. This measurement may teach it something new about the network. This is reflected by a shrink in the belief set, and this process repeats. In fact, we show that such shrinking is necessary for CCAs. If it happens to be that after a series of rate decisions and observations, the belief set still looks like this, then we can safely say this is a bad CCA. The belief set shows there's large uncertainty in the bandwidth of the network. So if the CCA is sending at low rate and the network turns out to have high bandwidth, then the algorithm would be causing underutilization. Alternatively, if the CCA is sending at a high rate, but the network turns out to have low bandwidth, then the CCA will be causing delays or losses. And this gives us a sketch to prove impossibility results in congestion control. If the only way to shrink beliefs is to violate some objectives, then we have to violate them. And so there's a fundamental trade-off in the objectives we're trying to achieve. So I've shown this picture of what the CCAs designed by our methodology look like. In the remainder of the talk, I'll describe how we fill in these 2 boxes, starting from the belief computation box. So recall I'd said we derive beliefs from a network model. So I'll give some brief background on what exactly I mean by a network model. So a network model is a mathematical description of how a network may delay, drop, or service packets. And past works in congestion control have often assumed an idealistic model of the network. They'll define some queue, link rate, and use simple deterministic or stochastic processes to describe the packet service. However, real networks are far more complicated. They consist of different network elements which may aggregate packets for performance reasons. They may need to negotiate when they can transmit packets if they're using a shared wireless channel, and more. All of these facets create variable delays in the processing of packets that have nothing to do with congestion. And recent work has shown if to this idealistic model, we just add a box that can delay packets arbitrarily up to some amount, then we can provably express the cumulative effects of these network elements. So using such network models, we derive belief computations. Right off the bat, the mathematical encoding of the network model first defines some variables that can be observed by the CCA, and also some internal state that is hidden from the congestion control algorithm. These non-observable variables directly form the dimensions of the belief set. Also, the mathematical encoding of the network model will use constraints to describe the possible ACK sequences an algorithm may receive for different choices of latent variables and sending sequences. If we just reinterpret what quantities we treat as known versus unknown, we can use the exact same constraints to infer what latents could have produced the ACK and sending sequence observations of the CCA. This is exactly the definition of the belief set and describes belief computations. So now that the belief computation is set in stone, our design space for congestion control algorithms is much smaller. We only need to fill in this rate computation box. And this small design space allows us to tractably use techniques from program synthesis to fill in this box. So we use techniques from prior work to encode the network model into logical formulas, and we do the same for objectives like utilization, delay, convergence time, and so on. Then we use SMT solvers to symbolically explore congestion control algorithm executions under the network model to figure out what mapping from this belief set to rate can ensure our objectives on all behaviors expressed by the network model. We get as output synthesized programs that look something like this. They output rate decisions for input beliefs. Now, you don't need to read the exact details here, but the point is that they're short, human interpretable programs that we can directly implement in networking stacks such as the Linux kernel. And if you're curious, here, the red variables represent coordinates of some extreme points in the belief set. So just to recap whatever I've told, we start with the network model and objectives to describe our high-level specification. We then systematically derive the belief and rate computations to meet this high-level specification. All of our reasoning is done offline, and we obtain short programs that we execute at runtime. With our methodology, the CCA designer only ever needs to think at the high-level abstraction of network models and objectives. They no longer need to manually reason about low-level CCA mechanisms. So we used this methodology to design and evaluate congestion control algorithms for different network models and objectives. And in this process, we actually discovered a fundamental trade-off in the objective metrics we were trying to target. And we proved that trade-off using our belief set framework. In what follows, I'll briefly describe what the trade-off looks like and an interesting CCA mechanism we discovered to meet the trade-off. And I invite you to see our paper for more of the results. So specifically, we found a trade-off between amount of packet loss and the time to converge to the bandwidth of the network when the network has jitter or non-congestive delays and short or shallow buffers. The trade-off looks something like this. The more loss a CCA is willing to tolerate, the faster it can converge to the bandwidth of the network. So a congestion control algorithm like BBR causes order bandwidth losses, but can converge in time logarithmic in the bandwidth. And we'd expect algorithms like AIMD to converge in time, linear in the bandwidth, but restrict losses by a constant amount. However, jitter can actually break this. Jitter can create a burst in the acknowledgements, which can trigger a burst in packet transmissions, and in turn cause AMD to lose order bandwidth packets. And so we asked our synthesis tool, can we systematically build CCAs on different points of the Pareto frontier? The answer is yes. Our synthesis tool automatically builds congestion control algorithms that meet the Pareto frontier. We implemented some of these CCAs, and here I've shown the time series of rate decisions and queue occupancy and losses caused by one of the CCAs. To meet the trade-off, the congestion control algorithm precisely controls when and how long it's going to probe for bandwidth and drain the queue. What was different from traditional CCAs and what surprised us was its draining behavior. Typically, algorithms will use drains of queues to learn the propagation delay of the network. But here, draining is also a key part of the bandwidth probing process. Unfortunately, I won't be able to go into all the details, but I encourage you to see the paper if you're interested. In summary, we invent belief set. It summarizes the possible state of the network given the observations of the CCA. And it's a powerful tool to reason about congestion control and simplifies the design and analysis of congestion control algorithms. On the design side, it enables automatic CCA synthesis to meet a high-level specification. We don't need to make any ad hoc decisions. Everything is derived from spec. On the analysis side, the belief set allows us to both prove performance guarantees and impossibility results. With that, I'd like to thank you all for your time and attention, and I'm happy to take any questions.